you.
So I would first like to thank the organizers for the invitation, and thanks to all of you for being here. So today I'm going to talk about three families of objects, namely silting complexes, torsion classes, and cotorsion classes, and the relation between them. And then we'll see how we can generalize each of them to an appropriate higher setting. So let me start by fixing an algebraically closed field K, a finite dimensional K algebra lambda. Mod lambda will denote the category of finitely generated lambda modules, and proj lambda will denote the full subcategory of projective modules. And then in this setting, it was proven by Adachi, Yama, and Reiten that the poset of two-term silting objects in lambda includes into the poset of torsion classes in the module category, with the image given by the set of functorially finite torsion classes. And then it was shown by Costello and Zonarova that the zeroth cohomology functor H0 gives a map from the set of cotorsion classes in this two-term homotopy category of projectives to the set of torsion classes in the module category, which restricts to an isomorphism between complete cotorsion classes and functorially finite torsion classes. And then it was later proven by Garcia that the original map between the bigger sets is also an isomorphism. And so we get this nice commutative triangle of isomorphisms of posets. And moreover, it is a well-known fact that torsion classes in the module category, they form a lattice, which have been studied a lot in the literature. They are known to be semi-distributive. For AN, they are the Cambrian lattices, and so on. And so what we want to now do is to replace this 2 in here by an arbitrary higher natural number. So, and we do this in the following way. So we fix a d greater than equal to 2. And we show that the poset of now d-term silting objects in lambda is isomorphic to the poset of complete and hereditary cotorsion classes in these longer homotopy categories. So complexes of projectives concentrated in degrees minus d plus 1 to 0. And then we show that the truncation functor tau greater than equal to minus d plus 2 gives a bijection between cotorsion classes in these longer homotopy categories to torsion classes in these new categories, which I call the truncated derived categories, which I'm going to define in a bit, such that this bijection takes complete hereditary cotorsion classes to functorially finite positive torsion classes. And so we again get this commutative triangle of isomorphism of posets. And what I want to point out here is that if I take d equal to 2, then this truncation functor tau greater than equal to 0 is the same as the zeroth cohomology functor. So this triangle for d equal to 2 restricts to the previous triangle that we saw. And finally, we show that the torsion classes in these truncated derived categories, they also form a lattice. And so the next thing that I want to do is to define what this category is and what it means to be a torsion class in here. So, okay. So this category d minus d plus 2 0 mod lambda, it's defined to be the full subcategory of the bounded derived category of complexes whose cohomology is concentrated in this interval. So it's a nice extension closed subcategory of a triangulated category. So it's extriangulated. And then we say that the full subcategory T in here is a torsion class if it's the left home perp of its right home perp. So if it satisfies this equation here. And I want to make a quick remark here, which is that if I take d equal to 2, then this truncated derived category d0, 0 mod lambda, it's just the same as the module category. And in particular, the definition of a torsion class here is equivalent to the definition of a classical torsion class, which is being closed under quotients and extensions. But somehow the definition is more difficult to generalize, so we use this equivalent version here. Okay. And then we say that a torsion class T is positive if there are no negative extensions between T and its perp. And finally, we show that even the positive torsion classes in these truncated derived categories, they form a lattice. In fact, they form a sublattice of the lattice of torsion classes. Okay, so these are the definitions. The next thing that I want to talk about is the following proposition, which is one of the key ingredients of the proof of the main result, and which says that the truncation functor tau greater than equal to minus d plus 2 actually gives an equivalence of categories between these truncated homotopy categories, so k minus d plus 1, 0 proj lambda, quotiented out by proj lambda shifted by d minus 1, so projectives in the last degree, and the truncated derived category d minus d plus 2, 0 mod lambda. In particular, if I take d equal to 2 in this proposition, this tau greater than equal to 0 is just H0. We saw that. D00 mod lambda is mod lambda, and we recover a classical result of Oslander, which says that the module category is equivalent to the two-term homotopy category of projectives quotiented out by the shifted projectives. And so now I want to end by looking at some examples. So let's look at the simplest example, lambda to be the path algebra of A2, D to be 3. Then we want to know what this truncated derived category D minus 1, 0 mod lambda looks like. So here lambda is a hereditary algebra. So by the result of Happel, we know that the Oslander-Ruyton quiver of the derived category is just multiple copies of the Oslander-Ruyton quiver of the module category. And in particular, the Oslander-Ruyton quiver of this truncated derived category is just going to be 2 copies of the module category. This will be true for any hereditary algebra. So you have the modules and you have the shift of those modules. And then one can sit and calculate all the positive torsion classes in here. They're all going to be functorially finite because there are only finitely many indecomposables. And this gives us that the poset of 3-term silting objects in lambda is isomorphic to the lattice of positive torsion classes in this truncated derived category here. And this is the lattice shown here on the right. It's an example of what are called Emery Cambrian lattices, which were introduced by Stumpf, Thomas, and Williams as one of the generalizations of Cambrian lattices. And the thing that I want to point out here is that it's not semi-distributive. So this is one of the first thing that goes wrong or goes different from the d equal to 2 case. Okay, and the next example that I want to look at is the Kronecker quiver. So let lambda be the path algebra of this quiver here. Then the lattice of positive torsion classes in this truncated derived category is shown here on the right. Well, the skeleton of the lattice, I have not labeled the vertices. And again, I want to point out 2 things here. So first of all, it's an infinite width lattice. So there are these 2 horizontal paths which are infinite. So, so it has an infinite width. And moreover, the lattice of torsion classes in the module category of the Kronecker quiver sits as a sublattice in this lattice here. And it's a general fact. So the lattice of torsion classes in the module category always sits as a sublattice inside the lattice of torsion classes in any of these higher truncated derived categories. And this begs the natural question whether or not we have a chain of lattice inclusions of this form. So tors mod lambda including into torsion in D minus 1, 0, mod lambda into torsion classes in D minus 2, 0, and so on. And we don't know this. So we only know that the first one includes into all the next ones, but we don't know if these inclusions at the next steps are true. Another interesting question that we can ask ourselves is if an algebra is tau tilting finite, that is, if it has finitely many 2-term silting objects, does it also have finitely many d-term silting objects for all higher d's? Again, we don't know this. We don't have a proof. We don't have a counterexample. And yeah, so those are a few questions that I want to leave you with, and that's all I have to say. Thank you for your time.